Hi, and welcome back to the final supervised learning video for this week. In this video, we're going to be considering principal component regression and partial least squares regression. Earlier this week, we've seen that when we have a large number of predictors, we can use penalties or constraints on our regression coefficients to regularize the regression problem and ensure that we still have a unique solution even when we have more predictors than we have available observations. In this video, we're going to consider a different approach, where we try and reduce the dimension of our covariate space to obtain a smaller number of predictors q than our number of observations n. We're going to try and go about this in an intelligent way so that we can still retain as much information as possible from our full set of p predictors. In our original regression problem, we represented points in our predictor space using a p-vector, where each component of that vector gave you the number of units in that covariate dimension that you have moved from the origin. What we'd like to do is come up with some other representation of points in this predictor space that again lets us represent any combination of predictors, but instead of our directions being chosen arbitrarily to align with the particular things that we're measuring, we'll have them instead align with the directions of greatest variability within our data. As you might recall from the applicable maths course, these are going to be the principal components of our predictors. So here in our first example, we can see that we can represent a particular data point as a times the unit vector e1 in the direction of the x-axis, at b times the unit vector e2 in the direction of the y-axis. Our data here has two principal components, epsilon1, which points in the direction in which our data is most variable, and e2, which points perpendicular to this original vector. Instead of expressing our data points as linear combinations of e1 and e2, we might instead express them as linear combinations of epsilon1 and epsilon2. This will give us a principal components representation of our data set. The thing that we particularly like about this representation is that it puts an ordering on our basis vectors, these vectors epsilon1, epsilon2, and so on. The majority of the variability within our covariates is going to be in the direction of epsilon1. Given that variability, the next largest amount of variability is going to be in the direction of epsilon2, and then epsilon3, and so on, all the way through to the direction of epsilon p, which describes the least variability within our data. This gives us a way of cutting down on the number of covariates that we're going to use within our model, and doing so in a structured way. We could use, for example, only the first q of these p principal components. In doing so, we'd still be capturing much of the variability from within our full dataset. And in doing so, we hope to capture most of the variability in our outcomes as well as in our predictors. So let's consider how this might work in the two-dimensional case, where we're wanting to go from two predictors down to one predictor. In this case, we're going to project all of our data points down onto the line that is spanned by epsilon1, and then we're going to use their positions on this line as our predictor within our linear model. This has reduced the size of our predictor space from 2 dimensions to 1 dimension. We can do exactly the same thing in higher dimensions, projecting down onto lower dimensional subspaces, where rather than the line here, we might have a plane or a hyperplane that each of our points in r to the p is being projected down onto. When we're doing this sort of principal component regression, it's really important that we standardize our predictors. This is because the scale on which each of our predictors are measured is going to influence the amount of variability that they have relative to the other predictors. So if, for example, we'd chosen to measure lengths in millimeters, the variation in those values is going to be much larger than if we'd chosen to measure the same lengths, but in kilometers instead. Standardizing all of our predictors in this way puts them on a comparable scale so we can compare the variability between predictors fairly. When we've got more than 2 predictors, we might then need to choose the value of Q that we're going to reduce our predictor set down to. This is a model hyperparameter and is chosen in exactly the same way as we've been doing for all of our other model hyperparameters up until this point. We're going to use cross-validation to do this. So this all seems very well and good, but what are some issues with using this principal component regression technique? Well, firstly, we're limited to linear transformations of our predictors. Each of our new basis vectors, epsilon I, is some weighted linear combination of our previous set of basis vectors. And therefore, each of our new predictors is just a linear combination of our old predictors, where we have to put some constraints on these weights here to ensure that our epsilons are actually unit vectors. This means that we can't remove any non-linear component in the variability of our predictors. So in this toy example, where we have a sinusoidal trend with a scale shift and a linear trend, we can remove the shift and the trend, but we can't remove this additional very clear structure that isn't linear in nature. We're also aiming to reduce the dimensionality of our problem by doing PCR. But that isn't really what we're doing here, because in reality, the probability of any of our original predictors being given 0 weight is going to be incredibly small. What we're actually doing is using a smaller number of predictors, but each of those is dependent on all p of our original predictors. So we're not actually reducing the size of our predictor space at all. This is analogous to ridge regression, where we reduce the size of many of our coefficients, but don't set any of them exactly equal to 0. This restriction on our weights, when constructing our new basis, is very similar to those constraints that we saw when doing ridge regression. So if principal component regression has these limitations, is there another approach we can take that might remedy some of these? In fact, there is, and it's called partial least squares regression. Partial least squares regression is kind of analogous to using boosting trees that we've seen before. The approach we take here is to repeatedly fit small models, take the residual of those models, and then fit further small models to those residuals, and to iterate this process, so that we're describing variability that we haven't described before at each stage. So to get the partial least squares components, and these are vectors just like our principal components before, we're going to start by setting our first set of residuals to simply be the standardized y values. To calculate the first component, we then consider each predictor j in turn, and regress what should say rk here on the jth covariate to obtain an estimated regression coefficient. We're going to do this for all p predictors, and then set our partial least squares component vector to be the weighted sum of our original basis vectors times each of those regression coefficients. What this is going to mean is that our partial least squares component is pointing in the direction in predictor space which has the strongest linear association with our current residual values. We're then going to update these residual values by taking off our estimated linear model, and then repeat this process q times to get q vectors which at each stage point in the direction of the greatest residual variability. This gives us q vectors overall, epsilon1 through epsilon q, which we can then use to fit a regression model of y on each of these constructed covariates. So with a little bit of effort, we can show that in each of these regressions, while we're regressing the partial residuals on each of the predictors, the corresponding coefficients are going to be proportional to the correlation between those predictors and the partial residual values themselves. It's this which gives us the fact that I stated before, that the partial least squares components are pointing in the direction of the strongest linear relationship to the partial residuals. And in particular, the first of these will be in the strongest linear relationship to the response itself. This sort of boosting methodology doesn't fix all of our problems, however. We can still only represent linear combinations of our original covariates in this setup, but what we can now do is truly reduce the dimension of our problem, because we can have original predictors which have zero weight within our set of constructed covariates or predictors. This means that we have a genuine dimension reduction technique. Including this response information when we're constructing our covariates means that the partial least squares regression technique often has a lower bias than principal components regression will. It also means that partial least squares relies more heavily on the training data than principal components regression does. That's going to lead to a model with lower bias, but with higher variability. It's going to be more sensitive to changes in our training data. Sometimes this trade-off pays off and results in better predictive power, and sometimes it doesn't. It entirely depends on context which of these approaches is going to perform the best. In the lab later this week, you'll get to explore some of these techniques in practice and actually implement some regularization and some dimension reduction. Implementing these methods is going to be really key to cementing your understanding of them and getting an intuitive feel for their behaviour. Thank you very much for your attention.